So in the last lecture we have seen that the energy expression, the relativistic energy expression given by E square equals P square C square plus M square C to the power 4. When we try to quantize this equation, similar to the Schrodinger's equation, by replacing the energy by I h bar del over del t and p the moment, by replacing this p by the momentum operator minus I h bar del over del x for a one-dimensional particle. And we have also seen for the 3-dimension, I think we converted it into 3-dimension, and we find that this leads to the Klein-Gordon equation, which is del square, not del square, this is the square operator, box operator, plus m square c square over h bar square. Okay, so psi equals 0, where this box, or this is sometimes also called the Lambertian. Okay, so this is given by 1 over c square del over del t square minus del square. Okay, and you can replace this by this, the square is missing. So we saw that when we solve this equation, okay, this give us similar kind of equation like the Schrodinger's equation, and this is called the Klein-Gordon equation. But when we try to find the density, the probability density, this was both negative and positive, because it contained terms like let me write the expression from the previous lecture, which was I h bar 2mc square psi del psi strict, or the psi conjugate, but del t minus psi del psi strict over del t. So we were not sure about that this psi is going to be positive or negative. It can either be positive or negative, but the probability density, the probability can never be negative. So this was not acceptable, and we know that the Klein-Gordon equation was not accepted as the equation, as a field equation. So now this was practically a challenge to arrive to convert this energy expression to a desired form. Okay, like for a non-relativistic particle, how the Schrodinger's equation gives us the required or the right results for the probability density. A similar kind of thing we needed from this, but this equation, the Klein-Gordon equation, which was failing to do so. So one of the great contributions from Dirac is it's converting this equation E square equals P square C square plus M square C to the power 4. So Dirac tried to write this in the form of a linear matrix equation, which is equals C alpha P plus beta M C square. So it looks like this, some kind of square root, taking the square root of this, but it's not exactly that, because you can see that if you take the square root of this term, this is there is no problem, but in the right hand side we have different. So writing this expression basically taking this square root path from this equation was one of the major contributions of Dirac, which he did by writing this in a matrix formulation where alpha and beta are matrices. We are going to explore this alpha and beta matrices soon. So what are these alpha and beta? So basically alpha and beta are operators such that it we are assuming some conditions which will further simplify our the format of the solutions. Okay, so for the simplicity we have assumed that alpha commutes with x and beta also commute with x. Okay, you can say that why we are taking these assumptions. Okay, so because we want that anything which is not commuting, okay, is that it is very important for the in quantum mechanics that that x and p operators actually do not commute. So now we are interested in the what is important for the point of view of physics. Okay, so so from the starting we are making us clear that alpha do not commute with x because it will create extra complications. Okay, so for the time being, let's just assume that these conditions are satisfied. Okay, and there is no problem in assuming variables which could satisfy any condition. Okay, we have assumed alpha and beta, these are arbitrary for now, and satisfying certain conditions. Okay, because if you do not take these conditions and go on solving, then further you will find that the solution could be much simpler if we take these conditions. Okay, people have solved it and they have realized that this will be better. Okay, so let's just assume this. Okay, and another thing is that it also commute with the momentum operator. Okay, equals 0 and beta and p. So basically these are not creating any kind of quantum hindrance for us. Okay, so let's now square this equation. Okay, I told you that one of the major contributions of Dirac is that writing this energy expression uh, in the form of this matrix notation. Okay, so there must be something peculiar about this equation. So let's square equation number, take this as equation number 1 and this as equation number 2. Okay, and let's now square this equation number 2 both sides. Okay, so squaring equation 2 both sides, we get, so let's see what we get. So in the left hand side we will obviously get e square. So e square will be given by the product of the entities in the right hand side. So c alpha p plus beta mc square into the same thing c alpha p plus beta mc square. There can be many questions in your mind that why we have taken C in the left hand side, not in the right hand side, because we previously it was in the right hand side. So C is the velocity of light, so it's a constant, you can take it any side. Okay, so there is no problem. And we have removed the difficulties of taking to the left or to the right. By from the beginning we have assumed that alpha and p are commuting, so either you take alpha dot p or p dot alpha, it doesn't matter. Okay, so let's just multiply term by term. So you will get first we will multiply these terms, so c square. Okay, and now you have alpha and p, so alpha and p whole square, multiply 2 times, so it will give you the second term is this. We will multiply this to this. Okay, so beta mc square multiplied by c alpha p. Okay, these two terms. Then we have this multiplied by this, so c alpha p multiplied with beta mc square, and then the last term beta mc square the whole square. Okay, so let's simplify this further. So if you simplify, you will get e square equals, so now this c square alpha dot p whole square plus this term will be let's write this as a second term. Okay, so this will be beta square, and this m and c are constants, so m square c to the power 4. Okay, and this is beta. So we are now get rid of the first and the last term, and now taking these two terms, m is constant, c is constant, so and this c, so let's multiply, take out all these terms, so it will be mc cube. Okay, mc cube, and the terms which are forming the matrix multiplication will be beta into alpha. Okay, and p. Okay, so these are the terms, and for this we have the same mc cube. Okay, then alpha, p and beta. Okay, so we know that alpha is commuting with beta. Okay, not p is commuting with beta and alpha. Okay, from these expressions, but we are not sure that alpha will commute with beta. Okay, so we are not assuming this. So okay, so can we simplify it in some certain appropriate way? Okay, so we can write it as alpha dot p. These two terms alpha p and p alpha, we can reverse this. Okay, so if I reverse this, we can get let's for some time we come back to the expression e square equals p square c square plus m square c to the power 4. Just for the time being, let's see. So now we will be comparing these two, the initial equation and what we get after squaring the matrix relation. Okay, so if these two expressions are representing the same squared of the energy, okay, so this if we take out this and we only have the square of p square here. So the coefficients must be equal. So if you take out this c square from these two terms, okay, so we have p square should be equal to alpha dot p whole square, and this means that this alpha square, okay, should be 1. So this is one of the things which we arrive. Another, we have this term containing the, I think there is some kind of issue. This is beta square m, this is m square, not c square, okay, m square c to the power 4. So if we compare these two, so the coefficients beta square m square should be equal to this m square, or simply you just cancel out and take this beta square equals 1. So we are getting the another relation. So we have two things, alpha square equals 1 and beta square equals 1. So one thing, if you approach is as this, that alpha dot p equals alpha x px, you can take split it into components, plus alpha y py. In 3 dimension, p has 3 components, px, py and pz, and alpha has 3 components, so plus alpha z pz, okay. So if you take the square of this, okay, no, if we take the square of this term, okay, so this will be a square of this, okay. So and this is equal to p square, okay. So this can give you, this can also give you that alpha square, alpha x square equal to alpha y square equals alpha z square equals 1. So let's just do this also, okay. So to just confirm this, alpha x px plus alpha y py plus alpha z pz, to take the square of this, we have to multiply this by the term itself, alpha x px plus alpha y py plus alpha z pz, okay. And so why we cannot just get the confirmation that alpha square equals 1? Because we know that this is not just a one-dimensional thing, okay. We need the expression in 3-dimensional, like the Klein coordinate equation. We may need the solution in 3 dimension. So that way, if we are confirming, we want to confirm that this is also true, this is also equals 1, because if you prove alpha square equals 1, that doesn't mean these terms are separately equal to 1. So for that you need to do this, okay. So when you multiply this, so you will get alpha x square px square plus alpha x, you have to multiply this with all these 3 terms, then this to all the 3 terms, so it can be a cumbersome task, and we are going to do some kind of algebra class for today, but it will give you some interesting result, okay, important for physics, okay. That's why Dirac, when first time Dirac solved this this equation, he got interesting results. Okay, because in the starting it gets some a little bit complicated and you may give up. Okay, I think before Dirac people may have approached like this, but in the midway they may have uh, thought that they might not get a satisfactory result. So I think this may be the reason that this work was pending after the Klein Gordon equation. Okay, so let's just multiply this with alpha x px, then alpha y py, then plus alpha x px, alpha z pz, plus let's write the terms in 3 lines. So this will be plus alpha y py into alpha x px plus alpha y py. This will be the square of the whole. You may also in doubt that why I've written like this, why I've not, okay, why I have not squared this. So you can do this and we can discuss why I am not squared. You can also take out these two things, like you can remove this two squares and write it as the product. Okay, and solve it in the next term. So this is the second term, and for the third term we have alpha y py multiplied with alpha z pz. And for the third line we have alpha z pz multiplied with alpha x px plus alpha z pz into alpha y py plus alpha z pz into, let's write like this, alpha z pz. Okay, so either you write as a whole square or like this. So why this term, you know that alpha and p commute, so there is no problem taking this square. Okay, so you can write it as alpha x square px square, and let's write all these three terms. So alpha y square py square and then alpha z square pz square, and the rest of the terms, okay, we can write this alpha x px, alpha y py. You can see that these two terms, okay, they are some kind of related terms, so we can write it together. Okay, so let's write in a single bracket alpha x px, alpha y py, then plus alpha y py plus alpha x px plus this term, this one, and this x and z. So this, so we can write it as alpha x px, alpha z pz plus alpha z pz, alpha x px. Okay, and so basically we are having one last bracket, okay, which is for this alpha y py, alpha z pz plus alpha z, this one alpha z pz into alpha y py. So that's it. We have written all the terms. So now we know that this is going to be, because alpha dot p whole square equals p square, and p square can be written as px square plus py square plus pz square. So this is we know that this is alpha dot p whole square. Okay, this term equals alpha dot p whole square. So if and this is equal to also p square from this. So now we can compare the coefficients of p square, py square and pz square, px square. So if we compare, we get that this alpha x square equals 1, this alpha y square also 1, and alpha z square is also 1. So this is the relation we needed, okay, for the three-dimensional case. So now what about these terms? Okay, because there are no other terms, so these things must be 0, or the sum of these three brackets could be 0. But over in inspection we find that these brackets should separately be 0, because let's just see about this. So you know that this px commutes with alpha. Okay, so we can take this out. Similarly, no, this is not plus, this is multiplied sign. Okay, there may be some mistake. Okay. So we can take out px and py and py and px to the left hand side. Let's just write this bracket separately. So if I take px and py outside the bracket, what we get? We get alpha x alpha y plus alpha y alpha x. Okay, because px now one thing we need to be clear, that px and py also commute, and you can guess this by as you know that what is px. So that's why we have taken this out, because you have here p, not px py. You have, in the first place we have py, then we have px, then so this is px py, and in the second term we have py px. So basically what we have done, we have written px into py, but that should be equal. I am saying that px py is equal to py px. So how this is possible? This is possible if py and px commute. So why they can commute? You know that px is equal to minus I h bar del over del x, and py equals minus I h bar del over del y. Okay, so if I multiply px with py, we get the multiplication of the two terms. So it will give you iota square h bar square del over del x into del over del y, and this will be equal to I square will give you minus 1, so minus h bar square del 2 over del x del y, and you know that this is equal to minus h bar square del 2 over del y del x. So it's now clear that and you can write it as just remove this. So you can write it as minus h bar square del over del y del over del x, which is equal to minus or simply py px. So we have proved that px py and py px commutes. So that's why we can take this to the left hand side. Okay. So we have written these terms. We are only writing this bracket for now. Okay. So this expression can be written like this. We have taken px py equals py px and taken this to the left hand side, taking as common, and now these three terms, all these three terms can be written like this, but we know that the terms except px square, py square and pz square, there are no terms. Okay, so these three brackets, the sum of these three brackets could be 0. Okay, and this is only possible if for our case, for this case, this is possible if these three brackets are separately 0. Okay, because somehow these z and y component and x components are normally orthogonal in sense, and the sum should be separately 0. Okay, so we can for now convince ourselves that this should be 0, because px and py cannot be 0, it can have some value. So obviously alpha x alpha y plus alpha y alpha x should be 0. Okay, so we have alpha x alpha y equals minus alpha y alpha x. Okay, so in the similar manner we can write for alpha y alpha z equals minus alpha z alpha y, and alpha z alpha x equals minus alpha x alpha z. So we can write these expressions. Okay, so now we have the recipe to write something further. Okay, so we have the energy expression written like C alpha P plus beta mc square. Okay, so now it's the time to follow the same recipe of replacing the energy expression by I h bar del over del t and P by minus iota h bar del over del x in one dimension, but in 3 dimension we should write minus I h bar del. Okay, so let's just replace these things in the above equation. Okay, the matrix relation written by Dirac. Okay, so if I write here I h bar del over del t, let's change the color. Okay, so I h bar del over del t equals, so this will be C into alpha into, for P we can write minus I h bar del. Okay, for P we have written, because this is P in 3 dimension, plus we have beta m c square. Okay, so we have replaced the energy and the momentum by operators, but you know that this expression is meaningless unless we apply it on some psi. So let's apply it on some psi. So this is going to apply over some wave function psi. Now this wave function must be in 3 dimensions, so it must be a function of the position vector and time t, r and t. Okay, so now we will write we can anyhow go, if we wanted to go further, we need to go with some trial wave function. So we will we will now further see how we can go by taking a trial function. Okay. So now the simplest of the wave function we can take is it could be psi r comma t, could be some psi naught, okay, into e to the power I over h bar p dot r minus et. Now you can think why this kind of expression has come. So I will tell you that let's not just think that we are putting anything which is just from our memory, or we know what we already have done, but I think we have not written the wave function still in from the lecture 1 to lecture 3. We have never written like this. So from where this kind of expression is coming? So I will not tell you that you just convince yourself that this can be the wave function. Okay, this can be a wave function because it seems to be very likely, but we will in our further lectures we will see why this can be the wave function suitable for this case. Okay, it's a very general expression because psi naught can be anything. Okay, but for now I will explain you how you can write this kind of term. In this lecture series we will I will assume that you know the wave mechanics from the quantum mechanics part, but I will not assume that you know the Dirac or the matrix mechanics. Okay, so because we will be discussing things from quantum mechanics also, and especially the Hilbert space and Dirac notations and the matrix mechanics. So whenever it will come, we will go into it, because there are people who come from quantum mechanics background, but they have only covered the wave mechanics part. Okay, so this series will be for those people also who wanted to go into the matrix mechanics, the Hilbert space. They are not introduced with the Hilbert space, so we will be doing in our further lectures. But you know that we have started that with the trial wave function as psi equals a e to the power I k x. Okay, you know that this is a wave function represented at any time t. Okay, we for any time t, the shape of the wave function, the function which describes the wave function at any given time t, like you are taking a picture of the wave function at any given time t, then the function which is describing the wave function could be written like this. But this is only a function of x. Okay, or you can say that at a time when you are taking this wave function, that is t equals 0. So basically this is x comma 0 which we were previously writing. Okay, now what we are doing, we are saying that the wave function has evolved in time. Okay, so we can write it as x comma t, and this x comma t can be written as a e to the power iota kx minus omega t. If you know a little bit about the wave in classical physics, okay, you know that the any wave can be written like this, okay. So but I will tell you that you just keep in mind that for this lecture I am telling you that you just assume this, that from where we are taking this expression, okay. But separately, okay, in this lecture we will go deeper inside this expression, why we write like this, okay. So because this is very important to go into the subject of quantum field theory, um, because if you do not understand from where these expressions come, why we write like this, why we should assume this as some kind of constant for now, because it can be a function also, okay. So for to extinguish a little bit the curiosity or the puzzleness of the problem, let me convince you that you can write like this, okay. So for one dimension, you know that what is k? K is the wave number 2 pi over lambda, okay. And you know that from the de Broglie's hypothesis, lambda is equal to h upon p, wave particle duality. A wave can behave like particle, and sometimes a particle can behave like a wave in the microscopic world. So if I replace this lambda with h over p, then k will be given by 2 pi over lambda can be replaced by h by p, okay. So this is 2 pi over h, no, let's write in a separate line, okay. So we have k is equal to, this p will go in the numerator and we can write it as h over 2 pi, and you know that this h over 2 pi can be written as s bar. So we have k as p over h bar, okay, this thing we have. So we can replace this k with this term, okay. So now psi x comma t can be written as a is some constant here, okay. E to the power I iota, k can be written as p over h bar. So now you can see that we are getting some this I over h bar and this p term, okay. So this is almost correct. Now we need this omega to be replaced by energy term, okay. So a wave like a photon or any wave packet, it has some energy E given by h nu, okay. So a wave can have energy in packets, okay. So for now there can be confusion like a particle with mass or just a photon, so we are not going deeper into this. We have reserved it for some later point of time, okay. So just write and get some, derive some expressions, okay, interesting, and get just trying to relate things, okay, trying to some we are trying to just extinguish our curiosity for the time being, okay. So E equals h nu, and you know that nu omega is 2 pi nu, the angular frequency. So we can write as nu as omega over 2 pi. So E can be written as this h into omega over 2 pi. So this could be written as h over 2 pi, this can be written as h bar, and omega. Okay, so we can write that omega is E over h bar, and this we can replace again here. Okay, so if we replace omega by E over h bar, taking the, so you can write it as a e to the power I over h bar p. Okay, and we have left the x. Okay, px minus et. And so for the three-dimensional case, we will replace this x with, okay, with the r, and this p with the p vector. Okay, so just this is not a satisfactory result because there are too many confusions here with this. Okay, but for the time, let's assume that we have some kind of you can say that some kind of connection to the to classical mechanics, how we write and wave in classical mechanics. So these terms can come from there. Okay, uh, we will discuss these things in detail later. Okay, so now it's the time to uh, put it into the previous equation, which is we have written here. Okay, so our job is to take the derivative of this expression with respect to time t. Okay, and then we will apply this operator on this. Okay, so let us simplify this. First we will calculate I h bar del over del t of psi r comma t. Okay, so this will be I h bar del over del t of the whole expression, which is psi naught e to the power I over h bar p x p dot r. Okay, minus et. We call it the phase which remains constant for a wave, for a propagating wave. But for the time being, let's just stick to this solving these expressions and these equations, and see what it finally gives you. Okay, we will derive the meaning and go into in detail how we can arrive this wave function. Okay, how these expressions come from classical physics, and what the difference in the expression from classical and quantum. So first thing you need to write is I bar. This is the psi naught term. So the derivative of the exponential will give you this is the same exponential e to the power I over h bar and p dot r minus et. You know that d over dx of e to the power x is e to the power x. So this we have used, but now the derivative, if you are differentiating e to the power y with respect to x, you have e to the power y into dy over dx. So whatever is in the exponential is becomes the y for you, and the derivative of this term, okay, we will be writing. So this will be I over h bar, and the derivative of this term with respect to t will be 0, because our we are taking t and r as separate variables, so we will not take dr by dt. You know that previously we have seen that there are no dx by dt terms or dr by dt terms in quantum mechanics. We calculate the expectation values of the terms, okay, the velocity or any term. So we will take it as independent variable. So this expression will be 0 and minus e into derivative of t will give you 1, so minus e. Okay, so this h bar will cancel with this iota, and iota will give you -1, and then multiplied with minus e will give you e. Okay, into psi naught into e to the power I over h bar p dot r minus et. Okay, and this is nothing but the expression itself. Okay, so this is e and psi r comma t. Okay, so in the left hand side, when this wave function, this operator acted on this wave function, this is giving you the e, and this is obvious because this is the energy operator, so the eigenvalue will be the energy. Okay, so now let's find the second term, which we will get when this c alpha, okay, minus c alpha h bar and this del operator, okay, or the nebula operator you call it. So minus c iota, okay, first thing is iota, c h bar alpha, let's just confirm it, minus iota c alpha h bar, okay, c alpha, and h bar is a constant, so we have taken it in the left hand side. So alpha and then the delta, the nebula, okay, and the wave function on which it will act. Okay, so psi naught into e to the power I over h bar and p dot r minus et. Okay, let me just confirm you that this is basically this expression, this operator will act on this, and then this will act on this. Okay, so we are calculating this term for now, how it will act on the wave function. So the constant psi naught will be in the left hand side, so minus I c h bar and then alpha, then this psi naught. Okay, we have written in the left hand side. Now the derivative of this, okay, with respect to this delta. So why this delta is, what is this delta? Delta is this nebula. Okay, so this is del over del x I cap plus del over, or x cap you can say, del over x cap, del over del y cap, then del over del z cap. Okay, so we will write it as del over del x cap plus del over del y cap plus del over, sometimes you write it I is k. Okay, you can write it, but it can confuse you because we are using iota for the complex root. So I over del z cap. Okay, no, so this is the nebula, and it will act on this expression e to the power iota over h bar. Now what we are going to do, we are going to write this p dot r as px into x plus py into y, okay, plus pz into z, because you know that this is a dot product, so it will resolve into the multiplications of the components and then minus et. Okay, let me write it in a little bit, take some space, okay, because it's necessary that you write clearly. Okay, minus e into t. Okay, so after differentiating you will get minus iota c h bar alpha psi naught. Now this there are three terms x, y and z, and if you if this term will act on this, the first term, okay, so the exponential derivative of exponential will be the exponential itself, okay, and then in the second term the chain rule will be applied, and the derivative of the exponent term will be done. So this will be done three times for this, the second term and the third term also, and for each time you will get the derivative of the exponential first, and so we can take out the derivative of the exponential, which will be e to the power I over h bar, okay, px, and for this time we can write it in the shorthand, the initial notation, which is uh, p dot r, okay, minus et. This term is same as this, okay. Now this term will act on uh, the exponent, the power. So when del over del x will act on px into x, it will give you the derivative of px with respect to x. It will take it will act as a constant, but x when differentiated with x will give you 1, and the rest of the term, these and these two terms when differentiated with respect to x will give you 0, okay, because there are no x terms. The derivative of y and z with respect to x is 0, so simply it will give you the terms. The first, the derivative of px into x with respect to x will give you px simply, and this x cap, okay, will remain. So for the second term, the derivative of this with respect to this will be 0, but derivative of this with respect to this will give you py and y cap, and similarly for the third term, pz into z cap, okay, and it is missing, and derivative of this et term with respect to any of this will be 0, okay. So you have minus I c h bar alpha psi naught. These terms become bulky, but you know that constants make the things easier for you, okay. So simply this I think we should include this and simply write this as, this is nothing but your psi naught, okay, this is psi naught, not psi I am writing, it is simply the psi r comma t, okay. So this is psi r comma t multiplied with this. What is this is simply p, okay, px plus py, so this will give you the p vector, but in our case we are writing it as p operator, okay. So I think this is not operator, because we are basically calculating acting the wave function already, okay. So this should be removed. This is simply the p vector, okay, and this is not operator. This will give you the eigenvalue p, okay. So now we can write it as minus I iota c h bar alpha p, okay, into psi r comma t, okay. So is anything we have missed? One thing we have missed, the derivative of this term I over h bar. So this thing I over h bar should be written, and I think this I will be multiplied with this iota, this will give you minus 1, and then it will become plus. So this plus 1. So I think I should remove this term. Okay, so h bar is also cancelled. So let's also remove this h bar and simply write it as C alpha p. Okay, C alpha, not p, yeah, C alpha p. Okay, C, h bar is also removed. So finally we get C alpha p into this term. So this is the eigenvalue we get. So with a positive sign you get. Okay, so now let's write the expression for one more time. So we have in the left hand side what we get E and psi. Okay, let me just show you once again. When you acted this term on psi, you got E into psi. Okay, so there we have calculated E into psi. So in the left hand side you have E into psi r comma t. Okay, and in the right hand side we acted, okay, this thing on this psi. You acted this term on psi. So what we got C alpha p psi r comma t, and then the last term we can write it as it is, which is beta mc square into psi. Okay, so plus beta mc square into the psi r comma t. We have done nothing with this because we don't know what is actually beta. Okay, so we have done the derivative thing only, okay, for the energy and for the momentum operators. Okay, so in the right hand side you can write it as C alpha p plus beta mc square into psi r comma t. So this is what we have got, that E psi r comma t is given by this. Okay, so now you can see that the energy eigenvalue you are getting, so this must be the Hamiltonian. Okay, you can call it Hamiltonian, okay, because this is giving you the energy eigenvalues. But if you do not want to go into that, you can just say that we are representing it by some h, but you know that it is actually the Hamiltonian. So this is C alpha p. You can take out C as common, so it will become alpha p plus beta mc. So this is the Hamiltonian. Now you know that Hamiltonian is like some kind of operator here. It's obviously an operator. So it is giving you energy as the eigenvalue. So anything in quantum mechanics, if you remember, any operator, okay, let's call it as O. Okay, if any operator O acts on some wave function psi. Now here I have used the Dirac notation of writing a wave function. This is a way of writing, and many of you are well aware of it. Okay, we will go into it. I told you that we will go into the Hilbert space and Dirac notation. Okay, why this is used in quantum theory and from where these things actually come. Okay, but in a separate class, on a different day, we will discuss about it. So when this O acts on a wave function, it gives you some eigenvalue written by you can write it as any term like alpha, or no, we can write it as some E value. Okay, E, and psi. So E is the eigenvalue of this equation. This is called eigenvalue equation. Okay, so any operator in quantum mechanics is used to measure something observable. Okay, so this puts a limit on this what kind of operators these operators can be. So basically, if you multiply by the conjugate of this in the left hand side psi, so this will give you the eigenvalue E, because psi and psi will give the one value. Okay, and it should give you the real measurement of a real quantity. So basically, any operator in quantum mechanics should give you real values, a real number, not a complex number. Okay, so the eigenvalue should be real, like the energy has some real value. The wave function in itself can be a complex quantity. Okay, but the thing which is used to measure the state, uh, what you finally observe, like energy, the momentum, whatever you observe, that observation is always real. Okay, so this imposes some condition on it, like uh, let's just discuss about it. Like for the case of Hamiltonian, okay, you know that Hamiltonian acting on some wave function gives you the energy eigenvalue. Okay, and for psi h, psi should give you the energy. Okay, so now uh, just to convince you what the next step we are going to take, because we are going to let's just do not surprise you, let us go with it. Okay, so if we take the complex conjugate of this, and because the right hand side we have energy which can be any quantity, but it must be a real quantity. Real things are measurable, and whatever we measure in quantum mechanics should be a real. Okay, so the operators should be in such a manner that it should give you a real eigenvalue, a real number. So if I take the complex conjugate both sides, so you know that energy or any eigenvalue which is a real number, the complex conjugate of this must be same. Okay, but okay, but this expression can be written as psi h Hermitian psi. Okay, but you know that the energy is also given as psi h psi. Okay, so from these two expressions we note that h dagger must be equal to h dagger. Sorry, h, not h dagger. H dagger should be equal to h. Okay, we took the complex conjugate of the real quantity, and that must be equal to the real number, because you know that any complex number z is written by a plus iota b, and you take the complex conjugate, it gives you a minus iota b, because the real numbers do not contain this quantity, so the complex conjugate will give you the same thing. Okay, and over the when you conjugate this, you get the h dagger, and then these two things should be equal to the same quantity, so h dagger must be h. So that's why in quantum mechanics you notice that the operators must be a Hermitian operator, because Hermitian operators give you the real eigenvalues. Any Hermitian operator, okay, when acted on psi wave function for a physical thing, should give you a real number, okay, multiplied with the psi. This is the eigenvalue problem. Okay, So the operators must be Hermitian. So we know that in quantum mechanics we have operators which act on some wave function and that give you some real eigenvalue. So with this curiosity in mind, because we already have this Hamiltonian expression, okay, H, we can to go further, let's just calculate the Hermitian conjugate of this H. Okay, so it will be, because C is a real number, so it will not affect the value, but this alpha oh, why sometimes it creates a problem. Alpha, what is there? Alpha into P plus beta MC. So we can take the dagger both of the sides. So it will give you C alpha dagger P. Okay. P, you know that P is a real quantity, so it must be the same. And beta dagger MC. Okay. So, but you know that H dagger is H for it to be an operator in quantum mechanics. You know that the operators must be Hermitian. So H dagger must be equal to H. So we have what we have. This quantity must be equal to that quantity. So alpha into P plus beta MC should be equal to alpha dagger P plus beta dagger MC. Okay, so this clearly shows that alpha should be alpha dagger. On comparison, clearly you arrive at this result, and beta equal to beta dagger. Okay, so this two things we now have, but you know that alpha has three things: alpha x, alpha y, and alpha z. Okay, previously we have already seen this. If you go somewhat back in time, so you know that alpha has three components. Basically, alpha is a matrix, the combination of matrices of alpha x, alpha y, and alpha z. So similarly, we can say that alpha x is equal to alpha x dagger, and similarly for y and z. So collectively, we can say that alpha I, okay, is equal to alpha I dagger. This is the one of the important expressions, and this is these two important expressions we have arrived. Okay, just by a very simplistic inspection from quantum mechanics. Okay, now we can move further by noticing one more thing. If you go back, do not remember everything. Okay, we have written one important result here. We have already arrived this. Okay, this is Py. So alpha I square is 1. Okay, and this implies that alpha I square is 1. And also we have seen that beta square, okay, if you go somewhat back, you can see that beta square here, and this beta square is also 1. So what are the things, the recipes we have already have with us? So we have alpha, these two things we already have. Let's write it in a sequence. So we have alpha I square equals 1. You know that alpha I has three conditions: x, y, and z. So alpha x square equals 1, alpha y square equals 1, and alpha z square equals 1. Then we have beta square equals 1. Then we have alpha I equal to alpha I dagger. Then we have beta equal to beta dagger. Means these are also Hermitian in nature. Okay. So you also know that any inverse of a function of a matrix is given by 1 over determinant of A into adjoint of A. Okay, if you remember, sometimes people write it as 1 over determinant of A and adjoint of A. Okay, so because you know that alpha I is equal to 1 alpha I square, if I multiply this term, okay, let's write it once again, and multiply both sides by alpha I inverse. Okay, this implies alpha I inverse into alpha I square equals alpha I inverse into 1, or 1. Simply you know that this becomes the identity matrix. Okay, so now this term can be written as alpha I inverse into alpha I equal to alpha I inverse. Now these two terms will give you the inverse multiplied with the same matrix will give you the identity matrix, and this is identity multiplied with alpha I will give you alpha I is equal to alpha I inverse. So this is one more important expression we have, and similarly you can do it for beta. So beta is also equal to beta inverse. So now we also have two more things in our list. Okay, so now you know that the determinant A inverse, if the A inverse exists, then determinant cannot be 0. Okay, that means it should be non-singular. Okay, so determinant of alpha I, okay, should not be 0, and I is your x comma y comma z. Okay, and similarly determinant of the beta should also not be 0. Okay, so over an inspection, what we get when you multiply this two expressions, we can I think one expression we have already done which is missing. We should also write it. Let me go back and see it. Yeah, these three expressions. Okay, we have written that these three should be 0, these coefficient you have seen. So what is this? So it says you that alpha basically we have already written this, but not for beta. Okay, we want alpha I into beta. So we want to check that if alpha I beta, what it gives. So I think we should go back and see this for the first time when we were comparing the energy expression. Okay, so we compared the P squares, these coefficients. Then we know that this MC cube term, okay, and this MC cube, there are no such terms in this expression. So the sum of this should give you 0. Okay, so let me write it here. Okay, so you can say that this beta alpha p plus alpha p beta should be 0, and then let me erase these terms. Okay, so we can take out p as this beta p, not beta beta. Okay, so this is p beta, sorry, this is p into beta. So take out p as common, and then you have beta into alpha plus alpha into beta equals 0, and you have alpha beta is equal to minus beta alpha. So you have one more thing also which we missed in our first step. Okay, so now we can write it here. Alpha beta, okay, is equal to minus beta alpha, and you know that alpha has 3 components. Okay, so alpha has 3 components, which is, so that's why we have written with the I subscript. Now if you take the determinant of this, okay, take the determinant of these two, both hand sides. Okay, so determinant of this alpha I beta should be equal to the determinant of this beta alpha I, okay, with minus sign. Now whenever you take a determinant, you should be cautious about this negative sign, because it can be replaced with a negative of the unit matrix. Okay, so you can write it as the determinant of alpha I, okay, into determinant of beta is equal to determinant of, there is minus sign, okay, minus 1 is going into determinant of alpha, sorry, beta, and then determinant of alpha I. So now it's very clear that these two terms should be cancelled out. Okay, because these are basically numbers. Determinant gives you numbers. So what you have is determinant. Okay, what you have is the determinant of minus 1. Okay, should be, it's not actually 1, it should be unit, should be equal to 1. So you have to imagine a unit matrix, okay, a unit matrix whose determinant should be 1, but that unit matrix can be one dimensional, sorry, 2 dimensional or 3 dimensional, or any higher dimension. Okay, so we are not sure about it. So how can we be sure? So we know that if you take the determinant of this matrix, this minus unit matrix, okay, so minus unit matrix will give you a negative sign, and that negative sign will make these ones as minus 1, minus 1, minus 1, minus 1, and so on, if it is a higher dimension matrix. Okay, so if you take the determinant of this, you know that for the first term you will take out these and take out minus 1 and take the determinant of this. Okay, and let me show you by doing this. Okay, let's suppose we have a 5 cross 5 matrix. Okay, so we have minus 1, 0, 0, 0, 0, then 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 0. Okay, and if you take the determinant of this, so what you will get first, you will take this, okay, and give a cross, then -1, and take the determinant of this. And to calculate the determinant of this, you will take this -1, and take the determinant of this. To calculate the determinant of this, you will take this, and then you will keep going like this. So if you have a 5-dimensional matrix, you will encounter these terms one time, second time, third time, fourth time. So we are going to have -1 to the power n, okay, but that should be equal to 1, okay, because these terms will also multiply in the last, so it will give you one more. You're thinking that 1, 2, 3 and this 4, but this will also multiply, so it will give you 5, okay. So you know that for now we don't know the dimension of what can be the dimension of this matrix, okay. So let's take it to be n. So -1 to the power n should be 1. This is a very important expression which we got from the mathematical relations. We are continuing from the expression of energy given by Dirac. So what this n can be? So this n can be should always be even to give you 1, okay. So n can be either 2, 4, 6 or any higher even number. N is even, okay. So now if we take n as 2, let's n as 2, okay. So for n, we need an expression like this. We must have alpha should be in such a manner, okay, that alpha into the matrices alpha should be anti-commuting. What I mean is that alpha x alpha y is minus alpha y alpha x, and similarly alpha y alpha z, we have already seen this, is minus alpha z alpha y, and similarly even alpha I beta is equal to minus beta alpha, right? So these are anti-commuting matrices. So in 2 dimensions we have anti-commuting matrices. The most fundamental are the polymatrices, okay. You know about polymatrices, okay. The sigma x, which is written as 0 0 1 1, then sigma y is given by 0 iota minus iota, and then sigma z as 1 minus 1, okay. Maybe wrong, if I have done any mistake you can check, okay. So these are matrices, and if you multiply alpha x and alpha y, sorry, sigma y, you will get -1. You will get alpha x into alpha y, not -1, and alpha y alpha x to be negative of this, and similarly for other terms, other matrices. So these are the known anti-commuting matrices, and separately we have independently the identity matrix, which is 1 1 1 0 0 1, okay. So we have these 3 anti-commuting matrices, the polymatrices, which we call, and these are very famous in quantum mechanics. So these matrices are anti-commuting, and any anti-commuting matrix in 2 dimension, okay, or 2 by 2 matrices, any anti-commuting matrices of this order can be written as a linear combination of these matrices. Okay, so but you know that there are only 3 anti-commuting matrices here. For this case we have only 3 anti-commuting matrices, but we know that n should be even, and for that case we have to leave this n equal to 2 case, but we cannot take n as 3, so the minimum value for n can be 4. Okay, so now you get the logic that we have n equal to 2, then we know that there are only 3 anti-commuting matrices. Okay, but we know that we need 4 anti-commuting matrices, which are alpha x, alpha y, alpha z and beta. We need 4 matrices which should be anti-commuting. Okay, but for n equal to 2 case we have only 3 anti-commuting matrices. Okay, so this will not work. So we can, if we want to get higher for n equal to 3, which is not possible because n should be even, so the minimum value for n becomes n equals 4. Okay, so for n equal to 4 case, for this case we will be going further and see what kind of matrices these are, how the properties of matrices which we already listed will help us to formulate something or to derive something new which we could not find using the Klein-Gordon equation. Will it give us it will be able to eradicate the negative values of the probability, okay, the rho. So we will see it in our next lecture. Okay, thank you.